At first, the room feels safe. Then one quiet click removes the only thing standing between her and the heat. She cannot see the danger yet. She feels it. The air stills. The wall warms, and the room gives the day back. 2,000 years earlier, another woman faced the same sun. She had no machine to fail, and no grid to bring it back. She could not create cold. Her house did something more patient. It blocked the sun and slowed the heat before it reached her.
Most people think Rome's secret was hidden beneath this floor. But the famous answer is exactly backwards. Ancient Rome faced the same Mediterranean sun, with no grid, no compressor, and no machine waiting to restart.
Yet behind some Roman doors, heat behaved differently. It did not vanish. It arrived more slowly.
You may have heard that the hypocaust was Roman air conditioning. That claim is not merely exaggerated, it is backwards.
The hypocaust burned wood and drove hot gases beneath floors. This system efficiently heated the entire building.
The hollow clay tubes in the walls were not wind catchers. They extended the heating system upward. Then where did relief come from? If Rome's most famous thermal machine produced heat, what kept a summer room usable? The answer was a sequence. Block the sun, delay the heat, release it at night, and move before it arrived.
First, stop sunlight outside. Once it enters, every surface inside must absorb it. Then use the wall. It was not cold. It was slow. And in extreme heat, slowness buys time.
The sun could strike the outside at noon, while the full temperature peak reached the room hours later. Now stop looking at the house for a moment. Listen to it. The courtyard did not refrigerate the house. It softened the small climate at its center.
And the most adaptable part of the system was not stone. It was the household, moving with the hour and the season.
For more evidence-based history, please subscribe to Lantern History. Then tell us below, which Roman idea should modern buildings bring back?
Vitruvius advised that summer dining rooms face north, away from the season's harshest direct sun.
The Roman ideal was not one perfect room. It was a house whose useful spaces changed with the season.
As sunlight crossed the house, people could cross it too, following the shade before discomfort became danger. The best time to defend a room was before it became hot of hot. Close the opening early, then preserve the night's coolness.
Awnings, deep openings, porticos, and shutters could place several layers between the body and direct sun.
Room depth mattered. The farther sunlight had to travel, the smaller the area it could directly heat.
Some prosperous households took the same strategy one level deeper, literally.
Below ground, surrounding Earth reduced daily temperature swings and blocked the room from direct solar exposure.
Archaeologists call some of these spaces aestiva loca, summer places, though the function is not certain in every case. A single house could offer several climates without trying to cool every room at the same time. But this strategy required something many Romans did not possess: enough space to choose another room. Architecture could delay heat. It could not make shade, water, and space equally available. Rome's builders drew heavily on volcanic tuffs quarried from landscapes around the city. They learned that different tuffs varied in strength, weight, water absorption, and durability.
Volcanic stone was not a magical refrigerant. The important thermal fact was mass, thickness, and time.
Protective plaster shielded vulnerable stone and changed how the wall met sun, rain, and air. Roman concrete combined mortar and aggregate into thick structural masses that could also store considerable heat.
A massive wall behaves like a thermal battery. It stores heat now and releases it later. But every battery can fill. At noon, the exterior surface takes the punishment first. Inside, the wall slows the peak, often preserving useful conditions through the most punishing hours. Thermal mass does not erase heat. It moves the hottest moment to a different hour.
After sunset, the house needed cooler air to carry stored heat away. The cycle worked best when night cooled the mass and openings closed again before the next heat load.
But when nights stay hot, the wall cannot empty itself before the next day begins. During a long heat wave, stored heat accumulates. The same mass that protected the room can delay its recovery. The Roman lesson is not immunity. It is time. Time before indoor heat becomes dangerous. Walls managed when heat arrived. Courtyards changed what happened after it entered the house. The atrium joined light, rainwater, circulation, and ventilation inside one controlled opening. The compluvium admitted daylight and directed rain into the house. Its thermal effect depended on sun, shade, and airflow. The impluvium was a collection basin, not an ancient air conditioning unit. In dry, moving air, evaporation could remove some heat from nearby surfaces and air.
Often the strongest relief came not from colder air, but from escaping direct radiant heat. Vegetation shaded surfaces, held moisture, and made the courtyard a more usable part of daily life.
A shaded body can feel far safer, even when the measured air temperature changes only modestly. Natural ventilation worked only when openings gave air a route through the house. With openings on more than one side, pressure differences could drive a useful cross-flow. Warm air also rises. Today we call this buoyancy, or stack effect. We can explain the flow with modern physics. That does not mean Romans knew Bernoulli's equation.
Builders did not need equations to notice which rooms trapped heat and which openings moved air.
A courtyard was not automatically cool. Too much sun, too little shade, or weak airflow could turn it into a heat trap. Height, width, orientation, openings, and vegetation determined whether the courtyard protected or punished.
One recent study proposes that some private bath suites also served as secluded summer retreats. The idea remains debated.
Online videos often claim Romans reversed the hypocaust and sent cold mountain water beneath the floor. The archaeological record does not support that as a standard Roman cooling system. The engine was fire. The cavity was designed to carry heat, not cold runoff. Tubuli were ceramic flues that extended the heated cavity behind vertical surfaces. They look like ducts. That visual similarity makes the cooling story easy to believe and easy to repeat. Romans moved water with extraordinary skill. But water engineering and underfloor heating were different systems. The real engineering is impressive enough. It does not need an invented air conditioner.
Roman concrete's durability does not automatically prove exceptional summer cooling. Research suggests hot mixing and lime clasts helped some Roman mortars seal cracks over time.
A material can be durable, strong, or waterproof without being a superior cooling material.
Roman builders chose tuffs for many practical properties. We cannot prove summer cooling was the reason.
Thermal mass is not uniquely Roman. The physics belongs to any sufficiently heavy, well-managed building. A basin could influence its immediate surroundings. It did not turn an entire villa into a refrigerator. Roman heat management was not one device. It was an interaction between architecture, weather, water, and people. One secret invention makes a better headline. The truth is more complex and far less equal.
The best passive options belong to households with multiple rooms, deep shade, water, and control over openings. Many urban residents lived in denser apartment buildings with fewer spatial choices. Upper rooms faced more roof exposure and often had less massive structure between occupants and the sun. Without opposing openings, natural ventilation could be weak even when the window was open.
A private atrium, peristyle, or summer room was not an ordinary urban entitlement. Rome distributed enormous amounts of water, but private convenience and decorative water followed status.
Passive architecture was not passive for everyone. Someone managed shutters, water, rooms, and daily routines. Seasonal movement works only when a household possesses more than one usable place to go.
Thermal comfort was partly an architecture of choice, and choice was distributed unequally.
Ancient sources and archaeology support seasonal dining rooms, especially in wealthier houses and villas.
Pompeii's housing record reveals a city of sharply unequal property and domestic space. Only a small economic elite controlled the city's largest and most adaptable homes.
For residents with one hot room, adaptation could mean moving a mat, not moving to another climate.
Rome did not solve summer heat. Some buildings managed it better, and some people had more protection than others.
The real lesson is not a lost technology. It is the connection between physics, behavior, and access.
Modern heat resilience begins with the same first move. Stop solar energy before it enters.
Thermal mass can slow indoor temperature rise and protect occupants during short disruptions.
When outdoor air becomes cooler, night ventilation can reset the building for the next day. A strategy that succeeds for one hot afternoon may fail during 10 hot days and warm nights. Heavy mass absorbs heat slowly, but after a long event, it can also release that heat slowly. Evaporative cooling works best when the air is dry enough to accept more moisture. An efficient winter envelope can still overheat in summer if solar gain and ventilation are poorly controlled. The goal during an outage is not luxury comfort. It is keeping indoor conditions survivable for longer.
Researchers call this resilient cooling, low energy protection against heat waves, system failure, and power loss.
The strongest buildings combine passive protection with efficient active cooling, rather than trusting one heroic solution. Modern atriums can use buoyancy and pressure differences, but now fire safety, wind, and controls must be engineered precisely. In a tower, stack effect can become powerful enough to create drafts, door pressure, smoke movement, and energy loss. Ground contact can provide another slow heat sink, the modern relative of the semi-subterranean summer room. Architecture does the first part of the work. Machinery handles what the climate and building cannot. When buildings need less peak cooling, the electrical system gains breathing room during the most dangerous hours. Return to the same blackout, but change the architecture before the machine fails.
The room still warms. It simply warms more slowly, and that difference can protect health. Across 2,000 years, the first defense remains recognizable. Control the sun before it controls the room.
The future does not require copying Roman houses. It requires using the same physics with better evidence and controls. Shade is often cheaper than removing heat after it has crossed the glass. Night ventilation needs secure openings, clean enough outdoor air, and a climate that actually cools after sunset.
A resilient building is designed not only for normal operation, but for the moment normal operation stops.
Heat protection matters most for people with the least money, mobility, health, or choice.
Thermal resilience cannot remain a luxury feature. It belongs in housing, schools, care facilities, and public policy.
Block, delay, release, move. The sequence is ancient. The obligation to make it accessible is modern. Rome offers no secret air conditioner. It offers a record of buildings negotiating heat through form, matter, and habit. It cannot promise comfort during every climate, every heat wave, or every social condition.
The strongest path is not stone instead of electricity. It is architecture, reducing how much electricity must do.
The machine may still stop. The question is whether the building continues protecting you after it does.
Rome's lesson is simple. The building should begin fighting heat before the machine ever turns on.